Hi, I'm Mark Barsamian with the Ohio University Math Department in Athens, Ohio. In this video, I'll be discussing what I call the neutral exterior angle theorem. This material is from section 6.3 of the book, Geometry, A Metric Approach with Models, second edition by Millman and Parker. More specifically, pages 135 to 137 are relevant to this material. And these four exercises are also relevant. Now, this section is called the exterior angle theorem. The theorem that I will introduce, the same theorem, I call the neutral exterior angle theorem. The reason I add the qualifier, the neutral exterior angle theorem, is that there actually will be another exterior angle theorem that we'll encounter later in the course. It will have a different qualifier. It will be called the Euclidean exterior angle theorem. But for now, in this section of the book, we'll be discussing what I call the neutral exterior angle theorem. All right, I'm going to start by recalling some old stuff that will be useful. From section 3.2, there's this theorem 3.2.6 that most students remember pretty well. This theorem says that if you're given two distinct points in a metric geometry, then there exist points C and D that create these betweenness relationships with A and B. The one that we'll be using today in this video is the fact that this point C exists out beyond point B on line AB. Another result we'll use from section 3.2 is something that was proven in a homework exercise. It says that if you have 4 points, A, B, C, and D, that have these two betweenness relationships, B is between A and C is between B and D, illustrated in this drawing, then those 4 points will also have these betweenness relationships. B will be between A and D, and C will be between A and D. That's illustrated, highlighted in this drawing. So in other words, if these two betweenness relationships are true, then all four are true, and that's denoted by this symbol, A-B-C-D. From section 3.3.6, we have the congruent segment construction theorem. It says in a metric geometry, if you're given a ray AB and you're given a segment PQ, then there exists a unique point C on that ray such that the segment AC that's created is congruent to this segment PQ that's given. From section 4.4 of the book, we'll be using the result of a book exercise. It was a fairly quirky result having to do with plane separation and interiors of angles. The exercise said this: given this configuration of points, triangle A, B, and C, points D, E, and F that satisfy these things, C has to be between B and D. E has to be between A and C. And E has to be between B and F. If those points satisfy all that, then one can say that F is in the interior of that angle ACD. Now, recall that in section 5.3, there was some discussion of bigger and smaller angles. First of all, in chapter 5, section 5.1, we learned about the angle addition axiom. It says that if a point is in the interior of an angle, then the angles that are created on the inside have measures that add up to the measure of the outer angle. Well, there's a corollary that's not stated as a corollary in the book, but it's an immediate corollary. It says this: if you have a point in the interior of an angle, then one of those angles on the inside has a smaller measure than the measure of the outer angle. And that comes from just looking at this equation. In this equation, the green x, the red x, the green y, and the black z are all positive quantities. So that means that that green number y is definitely going to be less than that black number z. So that is, this green angle, this inside angle, is going to have a smaller measure than this black outside angle. So as I said, that is a corollary, but it's not stated in the book. It's kind of obvious, but it's good to remind ourselves where it comes from. And there's a contrapositive of this unstated corollary that says if two angles don't have that inequality relationship, that is, if the measure of angle ABD is not less than the measure of angle ABC, then point D is not in the interior of angle ABC. So again, this corollary is not stated in the book, so the contrapositive of that corollary is also not stated in the book. Later in section 5.3, we had another theorem which is basically a converse of this. So remember that a converse of a theorem is not the same theorem. It's a different theorem. It has to be proven separately as a new theorem. So this is a new theorem. It says that if points C and D are on the same side of line AB, that's what's shown here, they're in the same gray half plane, and if measure of angle ABD is less than the measure of angle ABC, then D must be in the interior of angle ABC. Now there's an immediate contrapositive of this theorem. If this is not true, that is, if D is not in the interior of that angle, then this is not true. That is, the measure of angle ABD, it will not be less than the measure of angle ABC. Now notice that since the introduction of the concept of triangle congruence in section 6.1, the discussion in our course has been about proving that certain objects are congruent. Initially, our only mathematical tool was the side angle side congruence axiom. Soon, though, more theorems were proved that enlarged our mathematical toolbox. But those theorems were all about proving that certain objects were congruent. In section 6.3, we'll study the neutral exterior angle theorem. This theorem is extremely important. It's a new tool. It'll allow us to prove theorems about bigger and smaller objects. Whereas, again, we've been for a while now just proving theorems about congruent objects. This neutral exterior angle theorem will allow us to prove things about bigger and smaller objects. Section 6.3 starts with some definitions that are pretty self-explanatory. The idea of a so-called smaller segment, to say that some segment is smaller than another segment, just simply means that the first segment has a length that's less than the length of the second segment. So I would say this, the length of segment AB is less than the length of segment CD. And we'll also sometimes say this, segment AB is smaller than segment CD. Means the same thing. I won't use this notation that the book introduces to say that a segment is less than another segment. I don't see any point in saying that. I would like to say that some segment is smaller than another segment. And this notation is perfectly good. The length of one segment is less than the length of another segment. Same idea for a segment that's larger than another segment, referring to the lengths of those segments, and angles that are smaller than other angles, referring to the measures of those angles. Again, fairly self-explanatory notation and terminology. Finally, on to the neutral exterior angle theorem. First, the definition of an exterior angle of a triangle. An exterior angle of a triangle is defined this way. It's an angle that can be labeled as angle BCD in a configuration like this. We have a given triangle ABC, and we have a point D such that AC and D are collinear, and C is between A and D. So that's the definition of an exterior angle. The remote interior angles for this exterior angle are these angles. This is the remote interior angle, and this is also a remote interior angle. They're both remote interior angles for this one exterior angle BCD. The neutral exterior angle theorem says that in a neutral geometry, the measure of an exterior angle is greater than the measure of either of its remote interior angles. So this red exterior angle is bigger than this remote interior angle over here. And that red exterior angle is also bigger than this remote interior angle here. Now notice that I'm careful to color these remote interior angles in different colors. I'm definitely not saying that these remote interior angles are congruent to each other. They're not. You can see one of them is acute and one of them is obtuse. But they are both small compared to that exterior angle. All right, how do we prove this? Well, we start by saying, suppose that we have a triangle and an exterior angle. So we have to show that both of these things are true. Well, the proof is done in two parts. In the first part, we're going to prove that this holds, that angle BCD is bigger than angle ABC. That's proof part one. So we start by saying that there exists a point that's the midpoint of segment BC. That's a result from a homework exercise back in section 3.3. In a homework exercise, the term midpoint of a segment was introduced, was defined, and you had to prove that every segment has a midpoint. And a midpoint is a point that makes that equation, that congruence, true. Step 4 says there exists a point E such that M is between A and E, and such that ME is congruent to MA. Now, this is a single statement in the proof, and this single statement is often stated this way in proofs in math books at this level, but it can't be justified with just a single simple justification. You'll see that to justify this single statement, we actually have to make a couple of intermediate statements with justifications. Again, to get to this one statement takes a bit of work. First thing we have to do is we have to state that there exists a point P that makes this true. M is between A and P. That's using that earlier theorem about the existence of points with certain betweenness relationships. And then we can say that there exists a point E on ray MP. This point E exists that makes this congruence true. So you see now why we needed point P. We needed to introduce a point P because, well, the only way that we can say what we need to say here is to have a ray MP to be talking about. We are going to use our justification for this statement that we've made is the congruent segment construction theorem. And that theorem has to be applied to a given ray and a given segment. We had a given segment before. We had segment MA, but we did not have a given ray. So we had to introduce this point P in order to have a ray MP in order to say that there's this point E that exists on that ray. And then we have to go farther, and we have to be clear and say that points A, M, and E will have that betweenness relationship. M is between A and E. And to justify that, we have to talk about betweenness of points. That's back to concepts from section 3.2. I reviewed some of those in the introduction to this video. So again, remember our statement that we were trying to justify didn't even mention a point P. We had to introduce point P in order to get to be able to justify the thing that was stated. So that's a deceptively simple looking statement, kind of a nuisance to prove. Let's go on. So we've got this point E. Now we can say that angle AMB is congruent to angle EMC. So these two red angles are congruent. That's not surprising. Those are vertical angles, so we can use the vertical angle theorem. And then we can say that these two triangles are congruent. Triangle AMB is congruent to triangle EMC. They're shaded here in gray, and that's by the side angle side axiom applied to those two triangles. And you can see here in my drawing, I've highlighted the things that are congruent. There's one congruent side, there's our congruent angle, and there's our second congruent side. So in my drawings, I try to highlight the things and the hypotheses that enable us to say the conclusion. The conclusion is this gray shaded triangle is congruent to this gray shaded triangle. All right, statement 7 says that these two angles are congruent. Well, that's just by statement 6 in the definition of triangle congruence. You can see in my drawing here, I've left those two triangles highlighted in gray to remind us that those two triangles are congruent. And then I have highlighted just this particular pair of parts. Remember that the definition of triangle congruence is that all pairs of corresponding parts are congruent. All right, so we can now say that angle ABC is congruent to angle ECB. So that's drawn here in this triangle. This angle here is congruent to this angle here. That's the same angles we had in this previous drawing. That red angle and that green angle. I've just simply named the angles differently using this fact about different ways of denoting the same ray. The reason is these are the angles that we're actually interested in moving forward. All right, now we use that quirky result that I reviewed earlier in the video. We can say that point E is in the interior of this angle BCD by the result of that homework exercise. And then we can use that unstated corollary to say that since E is in the interior of this angle, then that green angle on the inside has a smaller angle than the big outer angle, smaller measure. So we have in this diagram, we have a big angle, big red angle, and a small angle, a small green angle. But remember, this green angle here is congruent to this green angle here. So that red angle is also bigger than this angle. And that was what we wanted to prove in part 1. Remember, in part 1, our goal was to prove this. That is, we were going to prove that this behavior is actually true. So that's proof part 1. Notice that after the introductory step, we had step 1 where he stated all the given stuff. We had 10 more steps to get to this result. It took us 10 steps to do this. Now remember, this proof was going to be in 2 parts. In part 1, we were going to prove that this picture is really what happens. In proof part 2, we're going to prove that this picture is really what happens. Now, since it took us 10 steps to do proof part 1, you might think that it's going to take us 10 more steps to do proof part 2. But the cool thing is that it won't. Proof part 2 is very short. We're going to prove that measure of angle BCD is greater than the measure of angle BAC. We start by introducing a point F such that C is between B and F. We can use that theorem from section 3.2. And then we observe that 2 vertical angles are created, a vertical pair, so they're congruent. Now, this is a very fun part of this proof. We can use the result of part 1. The part that we've already proven was about a diagram that looks like this. That is, it was about a configuration of points and angles, and we proved that an angle like this red angle had a greater measure than an angle like this black angle. So in other words, if you went back to the proof of part 1 and just did a clever change of letters, you would end up proving this, that angle FCA is bigger than angle ABC. But remember, this red angle FCA is congruent to this angle over here. So we can also say that this angle over here is bigger than this black angle. So I should have said here that that's the end of the proof. So notice, proof part 2 only took 4 steps compared to part 1, which took 10 steps. All right, that's the main topic for this video. What I'll discuss now is an immediate corollary of the neutral exterior angle theorem. So to do that, I'm going to start by going back to review some stuff from chapter 5 and chapter 6. Remember in section 5.3 we talked about the existence of a unique perpendicular to a line through a point that's on the line. So this theorem, theorem 5.3.5, says if you have this configuration, you have a given line and a given point that's on that line, a given line L, then there's exactly one line that does this. It passes through B and it's perpendicular to L. Exactly one line. Now in section 6.2, there is a related theorem about the case where you have a point B that's not on a line. So we have this configuration, a given line L and a given point B that's not on the line. Well, in section 6.2, the best we could say is there exists at least one line L prime that passes through B and that's perpendicular to L. All we could say was at least one. We were not able to say that there is exactly one. Well, the exterior angle theorem can be used to easily prove that if B is a point that's not on line L, then there cannot be more than one line through B that's perpendicular to L. This proof is so easy that the statement amounts to a corollary of the neutral exterior angle theorem, although it's not presented as a corollary in the book. So here's what I would call an unstated corollary. There cannot be more than one perpendicular to a line through a point not on the line. So if you have a point B that's not on some line L, then there cannot be more than one line that contains B and that's perpendicular to line L. The proof is simple. Suppose that you have point B, and you have one line that you know about that is perpendicular, and you've got some other line, M, that passes through B as well and intersects line L. You don't know whether that's perpendicular or not. Well, in fact, we can prove that it can't be. It cannot be perpendicular. Here's how it goes. Notice that this line L makes a triangle. And for that triangle, we have this angle here that's an exterior angle. Now, for that exterior angle, this angle over here is a remote interior angle. And so the neutral exterior angle theorem says that this angle has a larger measure than this angle. Well, that one red angle is a right angle. So that means that the green angle is less than 90 degrees measure. So that line M is not perpendicular. So again, we said, well, suppose you've got one line through B that is perpendicular to line L. I should have line L highlighted here. Then we can say very easily that there cannot be another line. So there is yet another unstated corollary. So, we had the earlier theorem that said in this situation where B is not on this line, all we could say in section 6.2 was there was at least one such line. Well, now we know there cannot be more than one. So the corollary is this, that in this situation where B is not on line L, there is exactly one such line. So this is really a corollary of two things. It's a corollary of that earlier theorem that says that there exists at least one line, and it's also a corollary of the neutral exterior angle theorem, which says there cannot be more than one. So therefore, there's exactly one line. So this corollary is not stated this way in the book. What is stated in the book is this corollary. Corollary 6.3.4 says that in neutral geometry, there's exactly one line through any given point P, perpendicular to a given line L. Realize when you read this that the book's corollary is actually encompassing two cases. It encompasses this case 1, where point P is on line L. That's this situation. Well, we already knew from Theorem 4.3.5 that in that situation, there's exactly one line L prime that passes through P, and that's perpendicular to L. But this corollary also encompasses this case, the case where point P is not on line L, and this corollary says there's exactly one line in this case as well. Well, that one corollary about perpendicular lines is all that I want to discuss about the implications of the neutral exterior angle theorem. We will be discussing more implications in a second video about section 6.3. Thank you.